Welcome to this explainer. Today, we're diving deep into the core mechanics of advanced JavaScript. If you've ever felt like JavaScript is just playing tricks on you, like variables mysteriously changing their values or the this keyword pointing to something entirely unexpected, well, you're in exactly the right place. We are going to evolve your skills today from basic scripting to true engineering. We'll map the entire journey of your code, starting from deep inside the V8 engine all the way out to advanced browser manipulation.
Here's our logical roadmap for this explainer. We're going to start inside the JavaScript engine with scope and closures, then zoom out to object-oriented prototypes. After that, we'll tackle asynchronous timing with promises, step into the browser environment itself, and finally, we'll cap it all off with the event loop.
All right, let's jump straight into Section 1, Engine Mechanics, Scope and Closures. So we have thankfully evolved past the old var keyword, and there's a really critical reason for that. It's function scoped, and it hoists in totally unpredictable ways. If you've ever written a simple for loop using var, and then later realized that your counter variable actually bled out into the rest of your application and broke something, yeah, you've experienced this bug firsthand. Modern JavaScript relies on let and const because they are block scoped. They safely lock your data inside the exact curly braces where you define them. It's just much safer, localized memory management. Honestly, you should always default to const and literally only reach for let if you know for a fact that the value absolutely needs to be reassigned later.
Now, building directly on that concept of block scope, we arrive at what I consider an absolute superpower in JavaScript, the closure. A closure is essentially a function that perfectly remembers the variables from the exact place it was born, and it remembers them even after its parent function has completely finished running and popped off the call stack. This isn't just fun trivia, right? This is exactly how you create true private state in your applications. When you write a function that caches previous calculations, a technique we call memoization, that inner function is using a closure to secretly hold onto that cached data long after the outer setup phase is done. It's like the function packs a little backpack of its surrounding environment to take with it.
And that brings us to a notoriously painful question. Why does the this keyword keep returning undefined? It's a bug that haunts pretty much every JavaScript developer. Imagine you've got this beautifully structured object with a specific method, but the second you pass that method to a click handler, suddenly this is undefined. Or even worse, it points to the global window object and wreaks havoc. Why does this happen? Well, it's because in traditional functions, the value of this is determined entirely by how and where the function is executed, not by where you typed it in your code.
In the old days, fixing this context issue meant littering your code base with awful hacks like var self equals this, or you had to aggressively chain the .binding method everywhere. But arrow functions completely changed the game here. They actually do not have their own this context at all. Instead, they operate lexically. That means they transparently inherit this from their surrounding scope. So when you use an arrow function for a callback, your context stays perfectly intact. No weird hacks required.
Okay, moving on to Section 2, the DNA of objects, prototypes.
Think about this for a second. If you create 10,000 arrays in your code, does the JavaScript engine create 10,000 individual copies of the .map or .filter methods? No, absolutely not. That would instantly crash your memory. Instead, JavaScript relies on prototypes. Every single object has a hidden internal link pointing to a parent object. It's literally genetic inheritance for your code. When you call a method, the engine checks your specific object first. If the method isn't there, it simply travels up this genetic prototype chain until it either finds the requested method or it hits null. It's incredibly efficient.
And here's the secret. This invisible prototype chain is the actual reality behind modern JavaScript classes. ES6 introduced the class, extends, and super keywords, which is great because it makes JavaScript look exactly like traditional object-oriented languages, such as Java or C#. But don't let it fool you. Under the hood, this is purely syntactical sugar. The engine isn't suddenly creating rigid, traditional classes. It is still brilliantly using the exact same dynamic proto-pull inheritance mechanism we just talked about. It's just wrapped up in a much cleaner, more readable blueprint for us developers.
Let's shift gears to Section 3, asynchronous timing, promises.
In the real world, things take time. Network requests, database queries, they aren't instant. In the early days of JavaScript, we handled this by passing functions into other functions, which quickly led to deeply nested, unreadable code known as callback hell. Promises totally rescued us from this. A promise is exactly what it sounds like. It's a guarantee from the engine that you will eventually get a result. It always exists in one of three specific states. It's either pending, it's fulfilled successfully, or it's rejected with an error.
By returning a promise, we can flatten our code, chaining asynchronous operations sequentially using .then methods, and we can catch any errors neatly at the very end of the chain with a single .catch.
But, the language kept evolving, and it gave us async and await, which is essentially beautiful syntactic sugar layered right over those promises. By simply placing await in front of a promise-based operation, like a network fetch, your complex asynchronous code suddenly reads like a simple, top-to-bottom synchronous story. The real magic here is that await pauses the local function's execution without blocking the main browser thread, so your UI stays perfectly snappy and responsive while you wait for your data to arrive.
That brings us to Section 4, the browser environment.
So, we are now stepping out of the core language and into the wild world of the Document Object Model, or DOM. When a user interacts with your app, say they click a button, that event doesn't just magically spawn at the button. First, it goes through the capturing phase, literally traveling down the DOM tree from the very top of the document straight down to the target. Then, in the target phase, it registers the actual click. Finally, the event bubbles back upward through those exact same ancestors. Understanding that events run on this two-way street is crucial because it allows us to intercept user actions at multiple different levels of the UI.
And we can actually use that bubbling phase to our massive advantage through a best practice called event delegation. Think about it. If you have a list of 1,000 items, attaching 1,000 individual click listeners will absolutely blow out your browser's memory. It's super inefficient. Instead, you just attach one single listener to the parent container. Because we know events bubble up, that single parent listener catches and processes clicks for all of its children. The best part? It automatically works for any new items you dynamically inject into the DOM later.
Now, an interactive app also needs memory. It needs state, and the browser gives us a few distinct tools for this. Cookies are tiny, holding just about 4 kilobytes, but their superpower is that they're automatically sent back and forth with every HTTP request, which makes them perfect for session authentication. Then you have localStorage, which is fantastic for simple string key value pairs, like indefinitely saving a user's dark mode preference. But when you need real power, that's where IndexedDB comes in. It provides large, asynchronous storage for complex structured data. If you're building a robust, offline-capable application, IndexedDB is your backbone.
Let's tie this all together in Section 5, the event loop capstone.
We've talked about closures, asynchronous promises, and browser UI events. But what actually dictates the exact execution order of all this code? Enter the event loop. I want you to think of the event loop like a hyper-efficient ticketing system in a busy restaurant kitchen. First, the engine runs all standard synchronous code straight off the call stack. Once that's empty, it immediately checks something called the microtask queue. This is essentially the VIP line, and it's reserved for your promise callbacks. The engine will completely drain this entire microtask line. Only when both the call stack and that VIP microtask queue are totally empty will the engine finally move on to the macrotasks, and that's where your UI rendering and set timeout callbacks live.
This perfectly explains one of the most common JavaScript interview questions out there. Why does a resolved promise execute before a set timeout that is set to 0 milliseconds? Well, it's because set timeout is a macro task, while promises are microtasks. Remember, the microtask queue is the VIP line. It always cuts to the front. The browser physically cannot update the DOM or paint the screen until your promise callbacks have completely draining. Once you deeply understand this hierarchy, you have total granular control over your application's performance.
So here's the takeaway. You are no longer just writing basic scripts. By mastering closures to protect your state, utilizing the prototype chain for efficient memory, wielding promises for asynchronous data, and commanding the event loop for precise UI timing, you've evolved into a true engineer. The advanced tools are right there in your hands. But here's the real question I want you to ponder as you open your code editor today. Are you letting the browser dictate your code's performance, or are you finally orchestrating the browser? Thanks so much for joining this explainer, and happy coding.